Hey everybody, welcome to another edition of Wine 3 Online. Today we're going to talk about closures as a little introduction and a little preparation for the trip to MA Silva. So let's jump right in. So, three types of closures. Traditionally, actually four types probably, or probably three types, some of which are traditional, and then a box. So traditional cork, of course, goes back hundreds of years. It's been perfected. It's really a great closure. It's pliable. Um, it lasts for many years. It can go 25 years and still protect the wine as long as you store the wine on its side so that it keeps the cork moist. But that pliability, that durability, and the fact that it lets in a little bit of oxygen makes it a great closure. Now, there's some problems with it, which we're going to talk about today. Because of those problems, people have come up with alternatives like synthetic cork, which has its own issues, screw caps, which actually are doing pretty well now as far as closures. What we don't know is their longevity, how well they'll do in aging wines over the long term. And of course, there's a box, which we won't talk about anymore, but it really is a great way to store wine because as you dispense from the box, the bag in which the wine is stored collapses and that protects the wine from oxygen. So if you just want a glass a day and don't want to open a bottle, maybe waste a whole bottle depending on how you store the bottle, boxes are a good way to go. But we won't talk about them anymore today. Let's talk about the issues with closures. We want to keep the wine fresh. Okay, so we want to limit oxygen entry. That's the main thing. We don't want to oxidize the wine. We want, at the same time, to prevent the formation of these reductive characters. So we need a little bit of oxygen getting into the bottle to prevent reductive characters, and I'll talk about that in a sec. Corks traditionally allow a little bit of oxygen in, and I'll tell you how screw caps have handled that. And then the third thing we want to do is prevent TCA or trichloroanisole, and I'll tell you a little bit about that in a sec. But it's the one that smells like a musty attic, and if it gets into your wine from the cork, it can ruin the bottle. So those are the issues. So we know a little bit about oxidation, right? We've talked about that on and off in class, and it's clear that wine, when exposed to oxygen, is going to get oxidized, and it'll end up tasting a little bit like apple cider. That's that aldehyde character that it gets. So we know that there's a problem with oxygen. What's kind of new is that there's an opposite problem, and that's not enough oxygen. And in that case, what we get is reductive aromas. So we can come up with smells like rotten eggs. So reductive would be the opposite of oxidative. So normally if we get oxygen in, we're going to oxidize the wine. The opposite is actually reduction, or reducing the wine. Now you don't have to worry about a lot of the specifics of the chemistry there. We may talk about them a little bit more as we go forward. But just think of reduction as what happens in the bottle when there's very little oxygen present. And these molecules here in the middle of the slide give you some insight into that. When molecules have this SH group, that's the thiol we've talked about before. We've talked about the fact that thiols are often stinky. They're often good stinky, like passion fruit, and they're often bad stinky, like rotten eggs, in the case of hydrogen sulfide, like is shown here. Last week at Moritzen, Clay talked about the fact that when yeast are stressed, they'll often produce hydrogen sulfide. He talked about some of the strategies for preventing that stress during fermentation. There are similar compounds to hydrogen sulfide. So hydrogen sulfide's here. They're similar compounds like dimethyl disulfide. So look, that's got a couple of sulfurs. If you actually break that disulfide bond, so there's two sulfurs there, we call that a disulfide bond right here. If we break that bond and we add a hydrogen on to that, each of those sulfurs, we end up with these two chemical compounds over here. So you see this is the left half of dimethyl disulfide, and this is the right half of dimethyl disulfide. after that disulfide bond has been broken, and then you add these two protons on to the sulfurs, the two of the arrows there. So here's the problem in a wine bottle. You can have some dimethyl disulfide. It doesn't have much aroma normally. Now it does have aroma, but its threshold is pretty high. So we often, when it's at fairly low levels in the bottle, we don't know it's there. If you break that disulfide bond, so you break here, and then you make molecules of methane thiol, that has a lower threshold for detection. And so once you cleave the disulfide bond and make methane thiol, now we can smell it, and it smells like rotten eggs. And that, of course, is a problem. Well, it turns out, so I'll go over to the next slide here. It turns out that breaking the bond and going from dimethyl disulfide to methane thiol, so going in that direction, that's a reduction. So, as it says here, it's a reduction. If you go back in the other direction and you form dimethyl disulfide from methane thiol, that is an oxidation. When we have too little oxygen in the bottle, we can have reduction. And we can go from dimethyl disulfide, which we don't smell because it has a high detection threshold, to methane thiol, which we do smell. So wine that goes into the bottle clean comes out smelling stinky. All right, so this is too little O2. So I tell you this story because, one, corks don't have the problem with too little O2. They let a little oxygen in the bottle. This was too little oxygen was a problem, however, for screw tops. Then that's been solved now by allowing a little bit of oxygen through the membrane inside a screw top. So you often hear of two different types of internal membranes in screw tops. Either you hear about tin, or you hear about something called Saranex, which is basically a series of membranes more or less based on saran wrap. Tin doesn't allow any oxygen in. Saranex allows a little in. In this table on the over here on the right side of the slide, it shows total, or it shows oxygen permeability here. And you can see natural corks are nicely permeable to a certain amount of oxygen. Saranex has a lot less permeability, but it does have some. And the fact that it has some means you prevent those reductive aromas in the bottle. So reductive aromas under a screw cap aren't the issue they used to be. For the cork, they've never been an issue, but with a screw cap they are. Now here's a problem with synthetic corks. Look at all these numbers. One, they're highly variable, and two, some of them are pretty high. So lots of times with synthetic corks, you can actually get too much oxygen in the bottle, and it's the variability that disturbs some people. Okay, so that's reductive, the reductive problem. So why not just use cork all the time? If it lets in a little oxygen and it doesn't have the variability of synthetic corks, why not just use natural cork all the time? Well, one issue is that when wine gets corked, it smells like a musty attic. And at low levels, that can be perceived 4 nanograms per liter. So we're talking about parts per billion, pretty low number. If you get up to 10 nanograms, you really get significant alteration of wine flavor. TCA, trichloroanisole, or corked wine, comes from mold contamination of corks, along with a source of chlorine. So we've talked about a lot of things that are made by microbes in the wine process. Some of them are good. Yeast make alcohol from sugar. That's a good thing. Yeast make nice positive flavors like banana aroma, those fermentation esters we talked about. Or yeast make passion fruit aromas like we talked about. So there are a lot of good things that microbes make. Malolactic bacteria do malolactic fermentation, also a good thing. Here's another example of how a microbe, in this case a mold, can make something and impart a flavor to wine, but in this case it's a bad thing. And it's trichloroanisole. And so how that molecule looks is it looks like this. So start with this six-membered ring, six-carbon ring with a couple of double bonds here, and anisole is this molecule here. So chemists will often use some kind of root word to explain something. So in this case, the root is anisole, and that I've drawn now is anisole itself. Well, when the microbes come along and they have chlorine, which is if they have chlorine available, and chlorine is often used to disinfect corks, they will hang three chlorine atoms, onto. My computer is acting up here, but three chlorine atoms onto this anisole, and you get 2,4,6 trichloroanisole. So that is a problem because it smells like a musty attic, and that's a problem in corks because corks can harbor live organisms like microbes. So how are people dealing with this? Well, I think we're going to find at MA Silva what they're doing is they are doing vertical integration. So they are owning the process all the way from removing the cork bark, and cork is just a tree bark. When they remove the bark from a cork tree, they're controlling the process all the way through to when they deliver it to the winery, the finished cork for putting in the bottle. So they can reduce the amount of TCA because they control the process and can keep chlorine away. So we'll hear more about that, I'm sure, at MA Silva. So that's the background. Here's the summary. Natural corks, they've been proved by tradition. They have slow oxidation. That's a good thing. They have some variability, not as much as synthetic corks, but TCA is the big problem. Synthetic corks are nice because no TCA. They don't harbor microbes. They can be sterilized, don't harbor microbes, so no TCA. But they're highly variable, so you get some oxidation. Sometimes you can even get reduction. That's a problem. Screw tops, no TCA, which is great. Controlled oxidation in the newer ones, that's really good. So it's taking care of the reductive, stinky, rotten egg smell. We don't really know how long-term storage is going to be with screw tops. Some wineries have tested about 10 years and they're happy with results, but we haven't looked beyond that. Okay, hope that helps, gang.